questions about the material? This week in lab, we're doing a TLC lab. Polarimetry sheets are due here. If you please turn them, pass them to the, Thursday lab first. Thursday lab.
False. Right.
Any other Thursday?
Some people aren't here yet.
Yes.
Okay, Friday lab.
Thank you all. Dr. Stevens. This Thursday.
Friday lab.
Make sure you get it.
Okay, guys, Alkynes.
Put it in the pile.
Alkynes, where are we at? Still at the top. Oh, previous page. Hydration of alkynes. Alkynes are only hydrated once. When you hydrate the alkyne once, you get an enol. Enol. Enols are not stable. Enols undergo rearrangement, tautomerization, and they actually give a carbonyl form. In this case, it would be a ketone. Mechanism for this. Welcome. Welcome. Okay, you can hydrate an alkyne using just aqueous acid. Mercury is often included. It's traditionally included always, but I'm going to do it without the mercury. H plus and water. Cation on left or right, cation on left, electrons here. Boom, boom, boom. And we get this carbocation intermediate. Water then adds. These electrons add to carbocation, and we get water added. 1, 2, 3, 1, 2, 3 here. Then lose the H. Something was here. This is probably like sulfuric acid. We have HSO4 minus. This can take an H, leave electrons behind. And this would give the enol. And we would reform H2SO4. My OH is up. This can be just flipped over, yeah? I mean, that's not stereogenic. That gives the enol, standard hydration of the alkene. Nothing really new there. Okay, how do we go from enol to keto form? It's just a rearrangement. There's no change in formula. These are thus constitutional isomers. Going from here to here is really not much new. We have an alkene. We also still have H+, because this is still the same reaction. Okay? What do brackets mean? Brackets mean that this structure is not isolated. It's an intermediate along the way. It's a neutral species, which could theoretically maybe be isolated, but it's not. So we put it in brackets. What's the mechanism for the tautomerization? First step is the alkyne. We're still under the same conditions. Acid is still present. Have we ever had an alkyne react with H+? Certainly. Are we going to leave cation on left or right? Left. Correct. So electrons pull away from the left card when we get here. By the way, what are we trying to accomplish? This carbon has two H's on the end. How many on the end here? 3. We got to get an H there. Well, right here, we're getting an H there. This gives new H there. There's now 3 there. Cation here, yeah? That's nothing more than an alkene reacting with H+. Nothing new. We've been doing that for over 2 weeks. Cation here because it's secondary, as opposed to putting it there, which would be primary. But just like when this was chlorine, what did we do when this was chlorine? What did we do when that was chlorine? You're looking on the previous page?
Yeah.
Good. That's a good place to look.
Yeah. Delocalize the charge.
Delocalize the charge by doing a process called anybody? Glad? Resonance. These electrons move down. We can show a resonance structure. Boop, 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 boop. Those move down, we make pi bond. There's an H there, there's only one lone pair left, and that's a plus charge. There's a new H there, yeah, it's there. These are resonance structures. Why are they resonance structures? Because all we did is move pi electrons. We didn't move any atoms. That's resonance. Well, look what this looks like. And if we just take the HSO4 minus and remove the H, leave the electrons behind, a lot of you are not showing this arrow here on your mechanisms. This makes a bond to H, but what happens to these two electrons? They stay behind as a lone pair. You need this arrow. What does this give? Well, it gives that. The oxygen now has 2 lone pairs, and we reform H2SO4 again. There you go. All we did was we reacted the alkene with H+, we did resonance, and then we took off. Because what do we need to do to get from here to here? We got to add an H here, and we got to take one off here. Add an H there, we do resonance, and then we take the H off there. And there's your rearrangement, called tautomerization. The tautomerization is actually it's actually catalyzed by H+, because the H+ is reformed. Tautomerization. These two structures are in equilibrium with each other, but usually the carbonyl form is highly favored. That's why this arrow is much larger. Now this one should really be about that big, because usually it's about 99.9 and this is 0.1%. That's typical equilibrium, or even more favored than the carbonyl form. So acetone in the lab that you wash your glassware with, predominant structure. Yeah? But a little bit of the small percentage of the molecules exist like this in the enol form. Tautomerization. Questions about the tautomerization? Pretty straightforward. There's a little mnemonic to remember the mechanism for tautomerization. Oreo. Oreo. What did we do first here? We put a proton on. Proton on. What do we do here? What is this?
Resonance.
Resonance. And what do we do here? The proton was taken off. Oreo. On, resonance off. Oreo. Under acidic conditions, you put protons on first. If this was basic conditions, it would be reversed. You would take proton off. Off, resonance on. Base catalysis would take proton off. Acid catalysis, you put proton on first. Oreo. Which of the following are tautomers of the compound shown? Anybody?
Second. First two?
The first two.
Yeah, first two. Those are your enol tautomers. Enol. The alcohol is not on the ene. That's not an enol. It's not an enol. That's not an enol. And these enols are, these are enols, they are tautomers of that. Why are they tautomers? Well, what's the definition of an enol? You all know the definition of an enol, right? That's why they're tautomers. Are the following, are the two down here below tautomers? Well, what's the definition of a tautomer? Are these tautomers or no? Sure they are. Tautomers. What's the definition of tautomer? You didn't come today without knowing the definition of tautomer, did you? Knowing that it was going to be the topic of discussion. Yeah, these are tautomers. And you're going from here to here, or you can say you're going from here to here. What's the difference? This H is relocated to here, and at least one pi bond has been moved. That's all this. It's relocation of one H and movement and relocation of at least one pi bond. Yeah, those are tautomers. Questions about anything there? Okay, let's look at hydration of an alkyne with BH3. Hydroporation. Hydroporation followed by a magic step. This would give this enol. And when this tautomerized, you would get the carbonyl form, which is actually an aldehyde. We can go through the mechanism. BH3, we're going to leave cation on left or right? Correct. So we would attack like this. Boom, boom, boom. Cation, but is it really formed? Or what happens at the same time?
Back.
This throws a hydride. Becomes BH2, and we have boom, boom, boom. Now these are trans. This could also be cis. B in carbon. I reckon this is E. It also gets Z here. I reckon it's not going to be important at the end. What's the magic step do? That's in step 1. Magic step replaces boron with OH. Yeah. And when you do that, what do you have? You've got the eno. So there's your eno. And then it undergoes tautomerization to give the carbonyl form. That happens to be an aldehyde. I just like to draw on the H's of my aldehydes. Of course, there's an H here.
Don't you see them?
Uh-huh.
What is that right below the plus? Is that?
That's supposed to be a Z.
Oh, okay.
So that's E, but it could also, we could have also shown the Z form.
Okay.
It really doesn't matter. Just like here, I mean, that is E, but you could also show Z. It really doesn't matter because the final structure is this, and that doesn't have any stereochemistry. There's no E or Z there. Ultimately, the product of this reaction is that structure on the far right, and it has no stereochemistry. Okay, so that's hydration of alkynes. Hydrate to the alkene, and then the enol undergoes tautomerization. We looked at the acid catalyzed mechanism for the tautomerization, which can be remembered with Oreo. Okay. Reduction of alkynes with hydrogen to begin with. The alkyne triple bond can be reduced with hydrogen, precious metal catalyst, again, such as palladium, platinum, or nickel, etc. We know that the hydrogen comes from the metal, and so if we show an intermediate where we just use one equivalent of hydrogen, we would get this product here. It would be an alkene, and it would be a cis alkene. That's because the two H's came from the same side, pushing the two methyls to the same side, and you get this cis intermediate. But that's an alkene, and we know alkenes react with hydrogen. So we can actually do the reduction again. And when you add two more H's, you get the alkane. And the alkane doesn't have any stereochemistry, so show it however you want. It's butane. There's no stereochemistry possibility. So this can be fully reduced to butane. Partial reduction would give the alkene, but importantly, it would be cis. Everybody understand why it would be cis? Because the H's come from the same side. That forces the methyls to the same side. It's a syn addition of hydrogen. Usually you can't stop here with precious metal catalyst. You have to go all the way, and so you really need two equivalents of hydrogen to go all the way to the alkane. Pretty straightforward reaction. Remember your stereochemistry of the intermediate. What if you wanted it to stop here? Well, actually, if you tried to just react with one equivalent, you would not get a good yield of this. Because you can't just say, hey, cis alkene, once you form, I don't want you to react again. Let's let all of this react here. It won't. Because as soon as 10% of this forms, then you have 90 and 10, well, then this can start reacting. It may be slower because there's only 10%, but once you get 50-50, the reaction's only going 50%, and you have 50 of this and 50 of product, well, then they equally react. You cannot get a good yield here. You typically have to go all the way. If you want to get a good yield here, can you do it? Yes. You do it down below. Use a poison catalyst. Hydrogen and poison catalyst, you can stop at the alkene. Poison catalyst. This is where you take one of your standard catalysts and you add something to it to poison it, make it less reactive. And actually, in practical sense, it does allow you to get a decent yield of the intermediate. You can stop here. Poison catalyst. Here's an example. You take palladium and you add like barium sulfate to it, or like lead sulfate. And sometimes these metals will poison the catalyst. Mechanistically, how does that do that? That's a little bit beyond what we can explain here. But they do that. Lindlar's catalyst is a poison catalyst. It's actually like the salt, quinoline. There's a variety of things mixed together. But if you see Lindlar's catalyst, that's a common poison catalyst. And when you see poison catalyst, it's typically to stop at the alkene. That's just about it. The only place you'll ever see a poison catalyst is this for this reaction right here. Of course, the alkene will be cis. But of course, cis is only clearly defined if there's only two substituents. If there's three substituents, well then, it's a little bit more than just being cis. But actually, you can't have three substituents. No, you couldn't have three substituents. You can only have two substituents. Yeah, so it would be as simple as just cis. I reckon we could, what if we only had one substituent? For example, what if you took that and did this? What would the product be? What is that, 1 butene? 1 butene hydrogenated with a poison catalyst? What would the product be? Get the alkene. 1, 2, 3, 4. Yeah. But does the alkene, is it cis or is it trans or what? Neither. It doesn't have cis or trans possibility. That doesn't mean that the two new H's here didn't come in from the same side. What if instead of H2 we use D2 and a poison catalyst? It would give that, right? Two deuteriums would be on the same side. Now that does have stereochemistry because the ethyl is trans to the D and cis to the H. So now we have E and Z. Is this E or Z? That's E. Because what's higher priority, H or D? D. Carbon or D? Carbon. E. Deuterium is an isotope of hydrogen, but the atomic number is the same. But the atomic mass, if the atomic number is the same, you use the atomic mass. And your higher isotope will take priority. So we can hydrogenate to a cis alkene using a poison catalyst. If you use a regular catalyst, you're going to go all the way to the alkane. Look on the very back. There's a synthesis. I'm not sure if this is what compound 1 is. Read. That's test 3 chemistry. No, actually, Vidic is organic 2. Organic 2, that's test 3. We're not going to cover this coupling. This is an Alkyne coupling reaction where they make this bond right here. Those coupling reactions won Nobel Prize in 2010. We'll look up that. Or reactions like that. But look at the final step in going from 3 to 1. What are they doing? The alkyne is being reduced to the alkane here. What are they using? Hydrogen and palladium carbon. So the final step is they're reducing the alkyne all the way to the alkane. Okay, so we know how to make a cis alkene. What about a trans alkene? Can we make trans from the alkyne? You can do it, but not by using hydrogen. Because when you use hydrogen, the H's come from the same side. That gives cis, right? Trans alkenes can be made from alkynes by this method, using sodium metal and liquid ammonia. Ammonia is a gas at room temperature, but if you cool it to negative 33 degrees, it will become a liquid. And you can actually use it as a reaction solvent. So this is sodium metal and liquid ammonia. Cold temperature. This is called a dissolving metal reduction, because we're using a metal and it will dissolve in the process. This reacts, this gives this plus what? What are the ultimate byproducts if you fully balance the reaction? So let's look at this mechanism. This is how you make trans alkenes from alkyne. This is actually our first look at a radical mechanism. Radical reaction. first consideration is if you take sodium metal and put it in liquid ammonia, it will actually give free electrons. The sodium will give up an electron. That's what it likes to do anyway, right? Doesn't sodium like to become +1? It will give up an electron. But the electrons are known to be sort of free. It's a very unique and interesting reaction outcome. And they're solvated by the ammonia. Maybe we can just show some, almost like hydrogen bonding. If you consider the ammonia all around the electrons, this is known as solvated electrons. Now, what does the sodium become after it gives up one electron? It becomes sodium ion. Now, this has a, very theoretical and like, what's going on here? How does this happen? Well, again, that's a little bit beyond us, but you can read about that. One unique thing about this is colorless at the beginning. When you add in the sodium, it becomes blue, the color of the ink here in the flask. Why is that color produced? It's a very interesting reaction. You can actually probably look online and see somebody adding sodium to ammonia and it turning blue. Can you imagine the first person to do that? And they're like, whoa, look at that blue. What happened here? Back in 1738, when that guy did that, maybe it was a woman. Somebody did it first. Oh. The people thought magic was going on or something. So, solvated electrons. This is the beginning. Now the electron goes into the pi system. You can just draw a single electron or something. Usually this is nucleophilic and we attack something. This is not an electrophile, it's an electron. Here, the electron pumps in here, and we use a fishhook arrow, a single hook. Okay? That's 2 electrons we're moving. That's 1 electron we're moving. It's a half arrow, like a fishhook. Okay? 1 electron. We've never just moved 1 electron before. We've always been moving either a pi bond, the 2 electrons of the pi bond, or a lone pair. That pumps in here, and these 2 electrons move over here. What does this electron arrow movement give, or electron movement give? I'll draw this up. Now, I have 1 electron here. 1 electron added here. Pi bond moved over here, so what do we have over here on the right curve? What does that arrow mean to you? We have 2 electrons over here. What's the charge of this species now? That's neutral. What's the charge of this guy? -1. If you react a neutral with a -1, what's going to be the -1? Well, what's negative? This carbon, it owns 5 electrons. It's only supposed to have 4. That's negative. That carbon is neutral. It owns 1, 2, 3, 4. But this is a radical. A Radical is an unpaired electron. I mean, this is essentially we produce radical in single electrons. Now, right here we have a choice. I could have drawn it, you know. We had a choice of how these two groups would move to. Would you rather have these like this or like this? Which one's better? Essentially cis or trans? Yes, this is better. The groups are opposite. Also, the electrons are opposite. This had a choice. And trans is better. That's why you get trans at the end. When we do hydrogenation, it doesn't have a choice. The two H's have to come in from the metal, have to come in cis. Okay, what do we have to get onto this carbon to get to that product? What needs to be added to this carbon to get to the product? H's. Yes. Where does the H come from? Only one place it can come from. Ammonia. It's the only place it can come from. This takes an H from ammonia. These electrons take the H. These electrons stay behind. Ammonia is usually a base. Well, here it's acting as an acid. And what does that give? We now have an H there, and we now have a single radical plus what? NH2 minus. Goes right here when these two electrons move on to nitrogen. There's now two lone pairs on the nitrogen. That's a minus. At this point, we need another electron here, another solvated electron pumps in here, and we get now two electrons. Now the charge is minus, and basically we're repeating the process. Now this takes another H from another ammonia. These electrons take the H, these stay behind. That gives final product plus another NH2 minus, and there's your product. So we pump electron in, we take an H, we pump another electron in and make this, and then we take an H. Question?
Why did you do the second part? Why did we pump another electron?
Where?
Oh, the second, like, why do we like, do it again? What was the purpose of that? Get it here.
Well, you got to have an H on each carbon.
Oh, okay.
How many equivalents of sodium does it take? Each sodium gives one electron. How many electrons did we need? Two. Yes. One electron came in, and then, yeah, we need two sodiums. How many ammonias did we need? Ammonia supplies an H, and then another ammonia supplies an H. How many of those did we need? Two. One of these reacts with 2 and 2 to give that plus what? What did we make here? We made 2 sodium NH2s. Now it's completely balanced. 2 sodiums, 2 nitrogens, 2 nitrogens, 6 H's. Well, yeah, if you don't count the methyls, 6 H's. 1, 2, 3, 4, 5, 6. Of course, NaNH2 is really Na plus and NH2 minus, right? Just like NaCl is really Na plus and Cl minus, right? So we made 2 sodium ions. That's because sodium gave up an electron twice. And we made 2 of these ions. There's 1 and there's 2. And you can show it sitting together as NaNH2. Now, the sodium is a metal, and metals are typically not dissolved, but this will quickly dissolve. And at the end, everything will be dissolved because this will be dissolved. And so the metal has dissolved, and thus it's called a dissolving metal reduction. This is pretty straightforward. It's a reduction in which a metal dissolves. Our first look at a radical reaction. Single electron arrow. This gives trans because right here we had a choice, and these groups are going to become trans as soon as this electron comes in. It's a little bit peculiar. Why would this electron come in? It's a little bit peculiar. I reckon a driving force of this is we're converting one of the pi bonds into 2 sigma bonds. But in terms of like polarity, dipoles, electrophile, nucleophile, it's not that clear why this would happen. But guess what? We know it does happen. And this is currently the best mechanism to explain it. Unless anybody has a better mechanism to explain it. This mechanism has not been disproven yet. And so in a lot of cases where you look at mechanisms, you got to remember that, well, we're asked, well, what proof do we have that this is the mechanism? In some cases, there's tons of proof. In other cases, the proof may be sort of limited, but that's all we have at this point. And so we're looking at this as our current theoretical thought. That hopefully has sound basis based on things we do know, as opposed to just saying, well, it's magic. Anybody have a better mechanism for how you get, you go to lab and do this, you will get that product. Do you want to just call it magic, or do you want to propose a mechanism? This is the currently proposed mechanism. Okay, last topic with alkynes is looking at the acidity of the terminal hydrogen. You're looking at a terminal alkyne. The H here has a pK of about 25. Okay? Well, that's not that acidic. But it's more acidic than an alkane or an alkene. It's enough acidity that we can do chemistry with. For example, if you take this molecule and treat it with N-butyl lithium, we can deprotonate the terminal alkyne and make butane. N-butyl lithium, it's just butane, normal being straight chain, that, and a lithium ion. This is about one of the strongest bases in organic chemistry. It's a carbanion. These electrons will take the H. These electrons stay behind as a lone pair to give this. When that takes an H, you get butane. Now you generate this. We're actually using one carbanion to make another carbanion. But this is more stable because what? Hybridization effect. Okay? In fact, if you look back at the acid-base hybridization, I showed this right here. We talked about how this is the most stable of the carbanions. So this gives you the more stable one, plus butane. How do you judge the acid-base? You got to know the pKa on both sides. This is 25. Butane is not acidic at all. Greater than 40. Which side's favored? Weaker acid. By how much is that side favored? That side's favored by 10 to the 15. What's that, about 100 gazillion? Okay. So, is N-butyllithium strong enough to deprotonate this terminal alkyne? Yeah, it's going to be pretty full. Pretty much complete. The equilibrium looks like this. I could draw it smaller. You need a microscope to see the other way. It's pretty much complete. So we can form the carbanion here. The alkyne carbanion. A lot of times these are called acetylide anions. That's sort of very generic, but IDE ending usually like chloride, hydroxide, anions. This comes from acetylene. Of course, acetylene is just that, with an H on each end. That's acetylene. Use torches. This is a gas. Now, it's a common name. What's the IUPAC name for this? Ethyne. You don't need a number. Ethyne. Nobody calls it ethyne. Acetylene. It's like the simplest alkyne. So that kind of comes from that. Now, that's got a group on it, but again, that's a very generic. Sometimes you hear the anions called acetylide anions. Okay, another base we can use, sodomid, sodium amide. Of course, like this is just like what we saw up top. This is sodium plus NH2 minus. What do you call a negative nitrogen? What do you call negative chlorine? Chloride. What do you call negative oxygen, like the OH minus? Hydroxide. What do you want to call this? Nitride might work. But it's actually called something else. Ammonia is an amine. How do you turn the amine into an anion? Not amine, but IDE. What is that? Amide? But that's not an amide, is it? What's an amide? An amide is a functional group, right? It's not an amide. Well, that's because the amide is two different things that are amides. A negative nitrogen is also called an amide. Confusing, yeah? Well, it's because of the IDE ending. So it's called a misnomer. This is called sodium amide. It's the simplest amine nitrogen anion. And sodium amide is often shortened to sodomid. Sodium amide. So have you ever heard sodomid? Okay. Sodomid is a common base in the textbook. In practice, it's a lousy base, terrible base in practice. But Is Tautomers strong enough to deprotonate the Alkyne? Well, you need to look at this. What do you get? What are your pKa's? And the next question is sodium hydroxide strong enough to deprotonate? Well, you need to look at that. Judge your pKa's. And then what is this? Miner's helmet. Everybody knows how to evaluate an acid-base reaction, right? Okay, please look at that. We'll finish that up next time. We're in pretty good shape. On Wednesday, we have a little time for review. Hopefully you'll bring some questions. Friday, we'll be starting new material, if not even on Wednesday. But I delayed the test until Monday to give an extra weekend. I don't like giving tests on Friday because you got lab going on. So we got a little time here. Okay? But this is the end of material. Have a good day, guys. TLC lab this week.